All right, so for today's lecture, we're going to dive back into where we left off at the end of Friday's class. So as a little bit of a refresher, what we are talking about, or what we started to talk about at the end of Friday's class, was regression estimation. So before this, we talked about ratio estimation, and we discussed that ratio estimation can be used for two different purposes: to estimate a population ratio directly, or to improve our estimate of a population quantity like the mean or the total by including information from a correlated auxiliary variable. Regression estimation serves the same purpose as ratio estimation, but only in regard to the second of those two objectives. What I mean is we use regression estimation as a tool to improve our estimate of a population quantity like the mean or the total. So we wouldn't see regression estimation as a tool for estimating a population ratio directly, for example. We're strictly using this in the second situation where we want to estimate a population mean or a population total. Regression estimation differs from ratio estimation as it incorporates an intercept term into the estimation equation. So ratio estimation essentially assumes that you have a straight line model that describes the relationship between the response variable and the independent variable or the explanatory variable, but that straight line relationship must pass through the origin. Regression estimation assumes that you have a straight line relationship that can model how the response variable changes with the explanatory variable, but the intercept of that model does not have to pass through the origin. Okay. All right, so on slide 41, we looked at an example of how to estimate the population mean using regression estimation. Now we have to go back and derive our estimate for the variance of the regression estimator for the mean. And then we can apply that formula here to find the variance of mu hat reg, or of mu tilde reg, for this particular illustration. So I'm just going to slide back to slide 37. So again, what we're doing now is we're going through our usual process of deriving the properties of the estimator that we are studying. So for our regression estimator, we have the following. So we have mu tilde reg is equal to mu tilde y plus beta tilde mu x minus mu tilde x. And let's call this, beta 1. Okay, so now we can write that mu tilde reg minus mu y is equal to mu tilde y minus mu y plus, and then we're going to introduce a zero term here, multiplied by mu x minus mu tilde x. Okay. And this term is equal to mu tilde y minus mu y plus beta mu x minus mu tilde x. This top part here should be a tilde, just so it's clear. Okay. Plus beta tilde minus beta mu x minus mu tilde x. All right. Now we can say, note that the rightmost term is a product of two small quantities. So if n is large, mu tilde reg minus mu y is equal to, is approximately equal to mu tilde y minus mu y plus beta 1, 1 mu x minus mu tilde x. Okay. Okay, so we've introduced a zero term. We subtracted mu y from both sides. Then we used a little bit of an approximation based off of large n to get a reduced form, or an approximation for the reduced form of mu tilde reg minus mu y. Okay, so we now have for a large sample size, mu tilde reg minus mu y is equal to mu tilde y minus mu y plus beta 1 mu x minus mu tilde x. All right, now what we can do is we can say, recall from SRS that, just move this down really slightly here, that the expected value of mu tilde y is equal to mu y, and the expected value of mu tilde x is equal to mu x. So the expected value of mu tilde reg minus mu y is approximately equal to the expected value of mu tilde y minus mu y plus beta 1 times the expected value mu x minus mu tilde x. Okay. So this term here is approximately going to go to 0. This term here is also going to go to 0. The reasons being simply that if we bring the expected value in, you now have the expected value of mu tilde y minus mu y, and then you have plus beta 1, the expected value mu x minus the expected value of mu tilde x. So that becomes mu y minus mu y, which is 0. And then it becomes mu x minus mu x, which is also 0. So now you have the expected value mu tilde reg is approximately equal to mu y. So therefore, the expected value of mu tilde reg is approximately biased. I think I can fit the whole word there. Okay. Okay, so now we're going to use a similar idea or a similar starting point to work out the variance. So we're going to go back to kind of taking advantage of what we had written at the beginning of this particular proof, and we can show the following. Okay. So following from above, we can write that the variance of mu tilde reg is equal to the variance of mu tilde reg minus mu y. Okay, so this thing will be approximately equal to the variance of mu tilde y minus mu y plus beta mu x minus mu tilde x. Okay, and then we can call this thing the variance of mu tilde e. And effectively, all we're really doing here is defining the residuals or the variance of the residuals from a linear regression model. Okay. All right. Okay, so essentially what we have shown is that the variance of mu tilde reg is equal to the variance of mu tilde subscript e. So the variance of the mean of the errors. Okay, so these are equivalent is the idea. And if you think back to standard regression analysis, where you would have, for example, y is equal to b0 or beta 0 plus beta 1x plus epsilon, for example, the epsilon is an error term that defines the distribution of the response variable, and it also defines the variance of the response variable. So that residual term introduces or declares that the variance of the response variable is sigma squared. So what we're going to do now is basically just show how we can estimate this term. But again, the key for us here is that the variance of the mean response or the mean estimator under regression estimation is equivalent to the variance of the mean estimator of the error terms. Okay, so this is a very similar idea to what we had in regression analysis. And in fact, what we'll show a little bit later is that these are identical terms. So we can take advantage of some of the things that we would have learned in simple linear regression analysis. So things we would have seen in the first and the second year level, and utilize those properties here. Okay, so to estimate this variance term, we'd need to define the residual, and then we just need to show how we can use the residual to find an estimate for the variance. So let little ei equal yi minus mu y plus beta 1 mu x minus mu x tilde. Okay. So again, this is basically just saying that the error term, the estimates of these error terms, which are the little ei, they're just the difference between the observed value of y and the estimated value of y. So this is an identical definition to what we would have seen when we first studied regression analysis. And by that I mean, sorry, like when we were introduced to simple linear regression analysis at the first and the second year level. So this is not an advanced topic that you would need, for example, stat 372 for. Okay, so then we can say the mean of y is equal to 1 over n, or actually I guess try and be a little more formal here. Okay, so the mean of y is equal to 1 over n times the sum across the frame of the ei. And then we can say that the estimator for y is going to be 1 over little n times the sum from I in S of the EI. Okay. Okay. And this thing is going to be equal to 1 over n times the sum I in S of the mu tilde y minus mu y. Wait. It's equal to, there we go. Yeah, there we go. Minus mu y plus beta 1 mu x minus x. All right. And then we can just note down, so we can show that the expected value of mu tilde e is equal to 0. And that would follow actually directly from what we had shown above. Because if we take the expected value of this, we're going to get mu y minus mu y, and then we'll have a mu x minus mu x term inside the bracket. So everything's just going to cancel out. And this is under a simple random sampling scheme. So as you can imagine here, we can also show that the variance of mu tilde e is going to be 1 over little n, or 1 minus n over little n over capital N multiplied by sigma of the errors squared over little n. So very similar form to what we had in the SRS case. Okay, and then what is the sigma squared e term? Again, this is basically just going to be the variance of the estimate of the variance of the residual. So we would have where sigma squared e is equal to 1 minus capital N, 1 over capital N minus 1 I in u of each residual minus its mean squared. So this is equivalent to 1 divided by capital N minus mu sum I in u of the yi minus mu y plus beta 1 mu x minus xi. Oh, sorry, missed this part here. Squared. And therefore we have that sigma squared tilde E is equal to 1 minus 1 over n minus 1 times the sum I n 1 to s of yi minus mu tilde y minus beta 1 tilde xi. Yeah. Well, and then just for clarity too, and sigma hat squared E then would be okay. And this is Q4, I think. Maybe it's Q5, I should check that. But that's the equation that we need for the regression estimator on assignment number 4. I just want to make sure I have the number right here. So that's going to be Q4. Okay. Okay, so on assignment 4, on assignment 3, in question 4, you have parts A through F. So part A, okay, so first off, you're given the data set directly. So it's a data set with 20 measurements in it. So it's a very small data set, or rather 20 observations, and there's 2 measurements each. In part D, you're computing the SRS estimator for the age of the trees. So this is only going to use one column of the data, and you're basically applying what we learned in lecture set number 2 of the course. In question 3, in part C, you're using the ratio estimation technique. Now, in this question, like in the first question, you have to compute the variances of the estimate based off of the estimating equations. So in part D, or in part C and part D, we have to utilize the expressions for the variances that we derived in this lecture set. So the form of the variance of the estimators is going to be identical. They're all going to be an FPC, which is probably going to cancel out, but I'll leave that to you to verify. So it's going to be an FPC multiplied by some variance expression divided by little n. So the variance expression from part B to part C to part D is going to change depending on the approach that you are using. Now, to calculate these is quite a bit of work, but you're not expected to do this by hand. What I would suggest you do is you use, for example, like Microsoft Excel or some sort of spreadsheet to calculate each of the variances. You'll notice that the marks for these questions are quite small. It's only three marks per part. So there's no expectation that you would do all of this calculation by hand. But in order for the estimators to work out properly, you do have to work out each of the different variances. So this is the expression that you need for part D. In the ratio estimation part, which is shown here, okay. So you can see here on slide 8, this is the expression that you need for part C, okay. And you have to work out each of these in order to get the 95% CI. So that's the purpose of the question. For part E, it asks you to label the estimators on the plot. So basically what you're going to do here, since each estimator is for the age of the trees, you'll have your scatter plot where you have age on the y-axis and you have the diameter on the x-axis. So the estimators are going to be an age value. So basically what you would do is you would just mark like a horizontal line on the y-axis to show the value of that estimator. So this is a little bit more of a computational problem than some of the other problems that we've seen before. So you're free to use any software that you're comfortable with, whether it be like Excel, SPSS, R, any of these things are fine. If you want to do it by hand, you can as well. But there's less chance of making a mistake if you do it via like a calculator-based program. Okay, so as per usual, the proofs took longer than I expected, but I should, I guess, probably be used to that by now. Okay, so now we have an expression for the variance of our estimator. So we can see that this expression for the variance is pretty much the same for you're going to need to be a little more specific, Parveen. This is my second line. Okay, so on this slide, this would be my second line, which I'm pretty sure is not your second line. So this line here is fine. Okay. So, okay, so now we're going to use our variance for the regression estimator, which is also shown on slide 39. So we did have this from beforehand as well. Yeah, 1 over n. Great. Okay, good. So that makes sense. Okay, so going back to the example that we left off with on Friday. So in this illustration, we're trying to predict average score on a test based off of number of hours of sleep. So we have two variables for each student, which is how long they slept the night before a test and the associated score on that test. So we left off by finding an estimate for the mean score on this exam. So now we need to find the variation that is attached to this estimate. Okay, so in this situation, we can show, okay, so we can show that sigma squared E is equal to 6.71, okay? And this is going to be done using what we just derived at the end of that proof. So this is going to be done by taking essentially the variance of the residual terms, or the variance of the residual terms for the regression line. Okay, so this thing here is actually equivalent to, so this is the same as the MSE. Okay. All right, so therefore, we will have that the variance of mu tilde reg, the estimate of the variance of mu tilde reg is going to be equal to 1 minus 15 over 68. Notice in this case that we can assume the FPC is going to be used because it's pretty clear that 15 over 68 is not going to be smaller than 5% of the population size. And then we'll have 6.71 divided by 15. And this gives us 0.3487. Thus, a 95% percent CI for mu is 74.633 plus or minus 1.96 multiplied by the square root of 0.3487, which is going to give us something in the area of 74. No, that doesn't make sense. Sorry, one sec. Gotta check this one. I'll also say too, like if anyone, when you're calculating the variances here, like if you want to check it or you want some help just with, I mean, so say you set it up and then you just want to make sure that you're doing it properly or check it, like feel free to send me like the sheet or whatever it is that you're using and I can let you know if you're on the right track with that calculation. This should be stuff that we're able to do fairly easily. But, you know, don't hesitate to ask me if you need some assistance with that kind of calculation, just to make sure you're not too far off. All right, so that's our first example of regression estimation. As we can see, this approach is, you know, it shares the same goal as the other approaches that we've talked about in the course in terms of estimating the mean. Again, the purpose here, or in the context that we've seen it, we have simple random sampling, and now we have 3 different approaches for estimating a population mean from simple random sampling. We have the direct approach, we have the ratio estimation approach, and we have the regression estimation approach. So a logical question that you might expect on the third quiz would be something like compare and contrast the 3 approaches. So what are the similarities between them in terms of, say, estimating a population mean? What are the differences between them? Okay, so being able to distinguish between between the benefits, or being able to distinguish between them would be beneficial to you for your understanding. Another thing that would fall out of that understanding or that ability to compare and contrast the approaches would be, when do I use which one, right? So what do we need there to be in order for the ratio estimation or the regression estimation approaches to be useful? Or when would we use regression estimation compared to ratio estimation? Okay, so being able to distinguish between them and to understand their similarities will benefit you going into that third quiz. Okay, let's look at another regression estimation approach or example. So in example 2, we have the volume of usable wood, which we're going to call Y, in a Douglas fir, which is a tree, is related to its basal area, okay, which is the cross-sectional area of the tree measured at breast height. Volume is expensive to measure because it requires that the tree is destroyed. Okay. To estimate the total volume in a section of forest that was to be sold, a sample of 25 trees was selected by dividing the section into small subsections. Okay. Okay, so a simple random sample of 25 subsections was selected, and then a tree was selected at random within each subsection. So if we treat this protocol as an SRS, the selected trees were sacrificed in the basal area and the volume were measured. All right, so we're gonna have 25 trees that were actually chosen from a subsection. That's the idea here. Okay, and we want to estimate or use our regression estimation approach to find an estimate of the mean, or I guess of the total in this case would be more appropriate, based off of the information that's given to us in the question. So we have the equation of the fitted line is yi is equal to 6.17 plus 1.51 times xi minus 1.31. And the residual sum of squares is 2.268. All right. Okay, so let's start off just by making some notes on what we have here. Okay, so what do we know? All right, well, we know that our sample size is going to be 25. That was made pretty clear to us from the problem. Okay, so we have our regression line here, right? So we want to estimate total volume based off of the basal area, I believe. Okay, so this yi here, this is going to be volume. And this xi here, this is going to be basal area. All right. So we have our sample size. We know that our estimate of the volume is going to be 6.17. That's from here. We know our estimate of the slope of the relationship is going to be 1.51. Okay. And then we know that our estimates of the basal area is going to be 1.31. Okay, and then each of these terms can be found from the regression equation. Okay, we're also told that the residual sum of squares is 2.268. So we also know that the sum of squares of the error term is going to be 2.268. Okay, so this will be from ANOVA for SLR. Okay, so that's from the ANOVA table for an SLR. All right, now we want to estimate the total volume in this case. So how can we do this? Well, one thing that we're going to need is mu x, and we're also going to need a population size. Okay, so let's suppose previous studies determined that capital N is equal to 56,800 with mu x equals 1.40. Wait, do I have this? Yeah, ux. Okay. Okay, so this is the kind of information, of course, like the population size and the mean of the population, you'd be given this on a quiz. This isn't something you would have to, guess or work out or anything like that. You'd have to have this beforehand. So let's suppose that this is the case then we can say that our estimate of the mean volume, oh, sorry, that would just be mu y. The equation started out in my head here. Oh, no, that was fine. Yeah. That would be the estimate from SRS. We're doing the regression estimator. There we go. Okay. So this thing is going to be equal to mu hat y plus beta 1 hat mu x minus mu hat x. That's going to be 6.17 plus 1.51 multiplied by 1.40 minus 1.31. Okay. And that gives us 6.31. All right, so then if we wanted to get an estimate of the total here, we can say so tau hat reg would be capital N multiplied by 6.31. And that would be do we have units for the volume? No, we do not have any units. Okay. All right. So the variance of mu hat reg is var hat mu tilde reg, that's a tilde, is equal to 1 minus little n over capital N sigma squared E divided by little n. Okay, so we can show in this case that 1 minus little n over capital N is greater than 0.95. Okay, so this thing reduces to sigma squared E over little n. And then what we can also show, here, I'll just move this down so I have a little bit more room. Okay, so what we can also show is sigma squared E is equal to the MSE. So this is going to be the SSE divided by n minus 1. It's not n minus 1 though, it's actually n minus k in that case. So that's going to be 2.268 divided by this is a regression line. That should be n minus 2. Okay, so that's going to be over 23. So that gives us 2.268 divided by 23 equals 0.0986. So then this thing is going to be 0.0986 divided by 25. Which is 0.0039. Okay. And I guess I'll just finish it here. So then we have the 95% CI for tau hat reg would be tau hat reg plus or minus 1.96 multiplied by n times the square root of the variance of the estimate of the variance of mu tilde reg. Okay, and then that's going to give us 358,408 plus or minus 1.96 multiplied by 56800 times the square root of 0.0039. 0.0039. And then I'll just finish this off real quick here. So 358,408 plus or minus 6. Okay, sorry, I went a little bit over time there today. So that's the second example of regression estimation. On Wednesday, we're going to talk about difference estimation, and then we'll talk about how to compare the estimates through a relative efficiency, which is the last thing that we need for question 4F. But ratio efficiency is a pretty straightforward idea. It's literally just a division of the variances. So this is something that you could do directly anyways. You would just take the variance from C and divide by the variance from D for part F. Okay, so as always, if you guys have any questions, let me know. Sorry about going a little bit over time today. And talk to you.
So the quiz is on the 22nd or 29th?
And I'll talk to you guys on Wednesday morning. Okay.